Hello, everybody. Great to be with you again. It's Professor Steve Rehse from the University of Windsor's Department of Physics, coming to you again to have another great DoD STEM K-12 Saturday. Very pleased to be with you on this last K-12 STEM Saturday of the year. It is May, and I have a really cool subject that we're going to be talking about today, the odd world of the black holes. A lot of people have heard about black holes, and you kind of read about these things in the media, and they're kind of out there, but nobody really knows what they are. So today we're going to really dive into that and see if we can understand what a black hole is and what makes them so strange in our universe. So, one of the reasons I picked this topic is that black holes are really very much in the news right now. At the time that I'm making this video, we have brand new images of a supermassive black hole at the center of the Milky Way galaxy. It's the first ever image of this supermassive black hole, and it's been in all the newspapers, it's been on the news. So black holes are really very much in the collective imagination right now. So this talk is really, really kind of timely, and that's kind of what motivated this talk to get into it. So in fact, here is that image. So this is the image of Sagittarius A star, which is the supermassive black hole at the center of our galaxy. This is courtesy of the Event Horizon Telescope. You can see that this is a really large object, about 24 million kilometers across. And this image is looking deep, deep into the core of our galaxy to find this thing about which everything else is rotating. And that's really, really exciting. And we do hope to talk about that at some point. But this image right now, this is May of 2022, very much so in the media at this time. So what I wanted to talk about in this talk, based on that news event, is before we can try to understand that thing that you're seeing in the news, I just want to see, can we actually understand what a single black hole is? Let's not worry about the supermassive black holes for right now. How about just the single, lone, traditional, normal black hole? And let's understand what it is, and let's see if we can figure out where they come from. And that would be enough probably for one day. So first, let us define it. Again, almost everyone knows the phrase black hole, but what is that thing, a black hole? Let's make sure we define it so everybody knows what we're talking about. First, a black hole is an object out in space, usually, so massive, and by massive, I mean not in size, not spatial extent, but mass, how heavy it is. So something so massive that it generates so much gravity that not even light can escape its gravitational pull. And most people kind of know that colloquial definition, but I find when I wrote that, there's a bunch of words in there. I'm not even sure exactly what all those words mean. So we're going to try to understand that. So in addition to being something so massive that light cannot escape its gravitational pull, there's always matter, things with mass, falling into this black hole that are constantly getting shredded and torn apart by these really powerful gravitational tidal forces, and they get crushed to an infinite density. And as well as that, at right at the surface of the black hole, the pace of time becomes very, very, very slow due to Einstein's general relativity. And we definitely don't have time to talk about that today, but that's another really weird thing that happens in a black hole. So that would be a whole talk unto itself. We just don't have time for that today. But I want to start with that definition about something so massive that it has gravity that not even light can escape. Can we unpack that? It's a bunch of words. We break it down and really understand it in a more simple way. That's what I wanted to do with you today. So here I have a little image. So this is something that everybody out there should know. Here is our planet Earth, and here is our moon. And our moon is in orbit around the Earth. And the reason our moon is in orbit around our Earth is that there is a gravitational attraction between our Earth, which is a big thing with mass, and the moon, which is a smaller thing, but still with a lot of mass. And gravity is this thing that exists in our universe that is a force of attraction between two things with mass. So a force means that they can push and pull on each other, and attraction means that any two things with mass are always attracted towards each other. As far as we know, gravity does not push anything apart. So gravity, anything with mass, wants to be attracted and pull them together. And of course, there's equations and mathematics you can do with that. But one of the simple rules you need to realize when dealing with gravity is that the greater the mass of either object is, the greater the force of attraction. So gravity is not a constant force. The stronger the mass of either object gets, the stronger that force is. So two things with very little mass are going to attract each other a little bit. The force will not be too strong. Two things with a ton of mass, the force of gravity is going to be really strong. They're really going to want to come together. So the force that's pulling things together gets bigger and bigger and bigger as the mass of either one of them gets bigger, bigger, and bigger. It doesn't have to be both of them, just either one of them. The more mass, the greater the force of the attraction of gravity. And that's how all of gravity essentially works. Isaac Newton worked out most of this mathematics and the definition of gravity a long time ago. And in fact, I actually have published another YouTube video about that, and here's a card for it, and I'll link right above it there. So a talk that I gave in April of 2021, Isaac Newton and his famous apple. So if you want to learn all about gravity and how gravity works in general, it's all right there in that video. So when you're done watching this one, go ahead and click on that, and then you're going to learn all about gravity right there. So basically, what this means that when the force of gravity gets bigger, when the mass of either gets bigger, it means that the stronger the force of attraction is, the harder it is to escape from that thing. Like, what if the moon wanted to fly out, you know, off into space, and it didn't want to orbit around the Earth? Well, the more mass the Earth has, then the greater the force of attraction would be. The greater the force of attraction, the harder it would be for that moon to escape. So if you wanted to actually pull on something and get it out of the gravitational attraction of that object, you'd have to pull really, really, really hard. And this is the reason that rockets have to blast off to escape Earth's gravitational pull. So if you've ever seen a rocket launch on TV, we always say 3, 2, 1, blast off. Well, what does blast off mean? Blast off means that to escape from the gravity of the Earth, the rocket has to go really, really fast. If you try and escape from the surface of the Earth and just go slow, you will never make it. And you all know this. You can do that physics experiment at home by trying to throw a baseball so fast that it will escape the gravitational pull of Earth, and you're not going to be able to do it. You've all probably thrown a baseball or any kind of ball up in the air, and this is what happens, right? So if you go outside and throw a ball up as high as you can, it'll go up and come back down. And the reason it comes back down is that your initial speed, the speed with which you threw it, was smaller than what we call the escape velocity. The escape velocity is the speed that any object needs to have to escape the gravitational pull of that object. In this case, it's the Earth. So a rocket, a baseball, whatever, they basically need to have the same escape velocity to escape the Earth. Now, I can go outside and throw a baseball up, and it'll go up and then kind of come back down. But if we get a Major League Baseball player, I bet you that person can throw a baseball way, way, way faster than I will. So it'll go up higher, 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 but still going to stop and turn around and come back. Because although he throws it with a faster speed, it's still not faster than the escape velocity of Earth. But if we launch a rocket can leave the Earth with an escape velocity greater, with a velocity greater than the escape velocity of Earth, and then it does never stop up in the air and come back. It just keeps going until it gets into outer space. And the escape velocity of Earth is about 11.3 kilometers per second. And that would be the escape velocity at the surface of the Earth. Note that if we can launch a rocket from 100 miles up, the escape velocity would be much lower. You're further away. You're already kind of escaped if you're further away. So you're further away from the thing with the gravitational attraction, the escape velocity is smaller. If you're very, very far away from the center, it has a small escape velocity. So if you were up on a satellite, Earth is still pulling on the thing, but you wouldn't need nearly as much velocity to get away from that satellite. So the further away you are from the center of that massive object, then the smaller that escape velocity would be. So it's not a constant everywhere in the universe. It has to do with how big the thing is, how massive it is, and how close to its center you are. So you can do some simple calculations for the mass of our Earth, the size of our Earth, and that's how you get this speed of 11.3 kilometers per second. Well, what if you could somehow be on the surface of the sun? Well, the surface of the sun is the radius of the sun is much, much bigger. The mass of the sun is much, much bigger. So the escape velocity of the sun is much, much bigger. It's 617 kilometers per second. If you could somehow get a rocket on the surface of the sun, but you probably couldn't because of course it would burn up. But that's just an example. There's another type of star called a white dwarf. Now, if you look at this, a white dwarf is actually not even as heavy as our sun. So if our sun is about 1 solar mass, a white dwarf is about 0.8 solar mass. So it's lighter. So you'd think the escape velocity should be smaller, but it's not, because look at the radius. So while the white dwarf is a little bit less massive, it's way smaller. So that means everything on its surface is really close to the center. And so escape velocity is really, really large. So here's an example where to have a high escape velocity, you don't necessarily have to be massive. You can be massive and compact or dense. That's going to lead to a very high escape velocity. What's more dense than a white dwarf? Well, a neutron star. A neutron star is another type of astronomical object. It has a mass of about 2 solar masses, which means 2 times the mass of our sun. But the radius is only 8 kilometers. It's the size of a small town here in Ontario, right? That's a really small star. It's twice as heavy as our star, but much, much, much smaller. So the matter inside the neutron star is really, really, really dense. And that means that the escape velocity is an amazing 250,000 kilometers per second. That's really, really fast. In fact, how fast is that number? Well, light actually travels at about 300,000 kilometers per second. And that is the fastest thing that anything in our universe can ever travel. We kind of call it the ultimate speed limit of the universe, which is why I have it inside a stop sign right there. One of the things we know about the laws of physics is nothing can travel faster than the speed of light. So it is not possible for anything to travel faster than 299,792 kilometers per second. And look, the escape velocity of a neutron star is almost equal to that. So if you understand what we're talking about, then it's not too hard to then think, if a neutron star has an escape velocity of 250,000 kilometers per second, if there is some other thing that's not quite a neutron star, maybe it's a little heavier, maybe it's a little more compact, if a thing anywhere in our universe exists such that the escape velocity, which you calculate based on the mass and the radius, if the escape velocity is larger than that number, 300,000 kilometers per second, then that would be a black hole. That's the definition of a black hole, even before you know what causes it. It's just a massive object that exerts a force of attraction due to gravity that has an escape velocity greater than the speed of light. By definition, that would be a black hole. So that's what that is. But before I get into like where these black holes come from, but let's talk about this. Like what is gravity? This is a strange thing. So let's talk about these forces of attraction. So here's just a short video I'm showing in the center of the screen. I just took a rubber band and I just like looped it over a doorknob there and I'm pulling on it. You guys have all done this. You can do this experiment at home. Take a rubber band and just pull on it or put it between your fingers and just stretch it like that, or take 2 magnets and push them together. You can feel that force of attraction. Just take a look at that again. So I'm pulling on this guy. As I was pulling, and I have this blue arrow here, and the blue arrow is showing, you can kind of see it's wanting to pull my hand back into the knob. I could feel that rubber band wanting to pull my hand back into the door. I could feel that force. And so it was very clear that was the elasticity of the rubber in the rubber band pulling against my hand that exerting the force. And that's pretty easy to understand. But what is the force in gravity? There's nothing in between it. Not only that, we have another problem. I told you that gravity is the force of attraction between 2 objects with mass, but light has no mass at all. Light should be completely unaffected by gravity. So even if we understood this idea of the escape velocity, it would say, okay, well, maybe a rocket ship can never escape from this object, but surely light can escape from it because light has no mass. And you just told me that gravity is the force of attraction between 2 things with mass. So light shouldn't be impacted at all, and yet it is. So what is this gravity? Because I don't see anything in empty space, right? Look at this. Here's this diagram again of the Earth and the moon. There's no rubber band between the Earth and the moon. There's no spring there. There's no air. There's no nothing. There isn't anything that exists between the Earth and the moon. But what is this force of gravity? There's nothing in between. And this is really, really puzzling. And so we understood what the force of gravity is, but where does it come from? And what's carrying that force over this distance? It's very, very strange. And so, of course, when we're confused like this, we have to turn to Einstein. Albert Einstein came up with this idea of finally a new interpretation of what gravity was. This idea that it's not a rubber band or a spring, but he used an argument that said gravity is actually a warping of the fabric of space. It's a bending or a curvature of space all around us. And gravity is a manifestation of the bending of the space around us. And then he started to realize that, well, if the mass of something goes up, the force of gravity goes up. And so what he understood that to mean is that the more massive an object is, the greater the warping of the space around that object would have to be. And then that will cause a motion which looks like a force due to gravity. So Einstein's general theory of general relativity actually explains this, and it's of course a very complicated mathematical theory, but actually it can be summed up in just about 12 words simply if you just want to understand what its implications are. And how we usually apply this theory of general relativity is just this: space-time tells matter how to move, and matter tells space-time how to curve. And I'm going to show a couple pictures of this that will help you understand it. So objects are moving all the time through our universe, but they are constrained to move through space and time, just like when you guys are driving on a highway. If you're driving on a highway, you are constrained to follow that road. And if the road makes a curve, you make a curve with it. You just go along with the ride. So we're living in a three-dimensional universe, or probably even higher dimensions, but as that dimensionality curves, you're constrained to curve along with it, even if you don't feel like you're curving. Space-time tells matter how to move through it, and then the matter that you put within space-time will actually determine what the curvature is. So let's take a look at a couple pictures of this that might illustrate it a little better. I can show it pretty easily in 2 dimensions. So if anybody's ever jumped on a mattress at home or dropped something heavy on a mattress, you know exactly what I'm talking about. Imagine a 2-dimensional surface, which is a mattress, and it has this purple grid on it. So everywhere on the purple grid, say it's like 1 inch between each of these intersection points. 1 inch, 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 no problem. But then you take this big heavy bowling ball and you drop it on the mattress and see how it bends or distorts or curves or warps that mattress down here. Look what happens. Do you think that that grid is exactly 1 inch apart anymore? You know it's not. Look at it. You can see it all stretching there. See how that grid is stretching apart? The distance between each of those points has changed because the surface, which used to be flat, is now warped. And that ball sinks into it. The ball has to sit on the surface, but the surface is just warped. That's how a 2-dimensional surface of space can be warped due to a heavy object being placed on it. If you can understand that, you basically understand what's going on with general relativity. Here's another illustration of that. This is applying one of Einstein's theories, was that not only does matter warp the space that it's sitting on. So now here's a 2-dimensional cushion again, say, on which I place 3 heavy objects, but the heavier the object, the more it warps that space. And that makes sense, right? So when we demonstrate this in our physics department, we actually just take stretched sheets of really stretchy nylon or cloth or kind of spandexy material, and you can stretch it between some tight surfaces, and then you drop these balls on it, and a light little ball will just make a small little depression. And a much heavier ball will actually kind of sit in there and stretch that material way into it. And this is the warping of that surface around the massive object. So the object warps the space in which it sits, and the greater the mass of the object, the greater that warping is. And this is an illustration, this one on the left, this is something you can almost do at home. Get yourself a nice piece of some really stretchy material, hold it tight on all the edges, drop something heavy in the middle, and you'll see it stretch. That's the warping of that material. We're living in a space-time which warps exactly the same way. Now, we live in a world of 3 dimensions of space, and that's not really easy for us to show you, but here are 2 illustrations of what it would look like, how space-time warps around a massive object. So on this previous slide, I had a grid, right? In the grid where it's unwarped, it's just nice uniform squares. Well, just imagine in a 3-dimensional space, the part where it's unwarped are nice 3-dimensional cubes. But now when I put a massive object in the middle, look at how those cubes distort. It's not a nice uniform lattice of square cubes anymore. It's kind of bent in towards the middle. The space is bent. The distance between all the points changes. And the lines between these points actually starts to curve. That's a warpage of space-time. And here you see an object moving through and how it distorts space-time as it moves through it. And here's just a stationary object where the space is moving around it, just to give you some idea. It's a really difficult concept to understand and visualize 3-dimensionally, but you just have to understand where the massive object is. Space and time are bent around it. Now, let me actually show you a good one of the implications of a warpage of space-time. For this, I'm going to make an appeal to Professor Brian Greene on a really good episode of What is Space? The Fabric of the Cosmos. And he's going to use this wonderful pool analogy to really show you how the warpage of space-time to us looks like the force of gravity. Check out Professor Greene here.
Now, if space-time were nice and flat, like the surface of this table, objects would travel in straight lines. But if space is like a fabric that can stretch and bend, well, this may seem a little strange. But watch what happens.
Bear with him.
If I put something heavy on the stretchy space-time fabric.
All right, see how it deforms and warps around it?
Now, if I take my shot again, the ball travels along an indentation in the fabric that the heavier object creates. And this, Einstein realized, is how gravity actually works. It's the warping of space-time caused by the objects within it. In other words, gravity is the shape of space-time itself. The moon is kept in orbit not because it's pulled to the Earth by some mysterious force, but rather because it rolls along a curve in the space-time fabric that the Earth creates.
So that's a whole new different way of looking at gravity. And once you understand that that's what gravity is doing, now you can understand how it's going to affect light. So it's not a mystical, magical rubber band that's going on and pulling the light back. Light is just traveling through space like it wants to do, but the space is just going to be curved so deeply that it can just never escape from it. So that way of visualizing it helps you understand. So now I'm finally going to get to the black holes. So we had to understand gravity first, but now we know enough to understand the black holes. We have seen if matter warps space-time, so here's our Earth, and again, if you pretend that it's on a two-dimensional grid, it distorts that two-dimensional grid like that. See, it makes that indentation. Or here's even a picture if you put it in a three-dimensional grid, and you can see how three-dimensional space is warped around that thing. So matter warps space-time like our Earth. What would happen if we put something really massive? So replace the Earth here with something really massive. It would look like this. Imagine that super stretchy pool table that Professor Greene was just talking about, and you put something on it that's infinitely heavy. And instead of making a little indentation, it makes this huge, massive indentation, right? Then you would get this huge warping or bending of that surface. And that's what we think a black hole is, right? It is something so massive that you've bent space and time so much that it kind of creates this potentially infinitely deep curvature here. So it is a warpage of space-time. It exists in a normal space. It is a concentrated amount of mass that have warped space and time so much that light can no longer get out of this region of space because it's warped and curved too strongly. All right. There was a physicist named Schwarzschild who thought about Einstein's equation, and he actually gave us some mathematics for what space would look like around a spherical mass that had a mass high enough to actually do something like that. And if enough mass was packed into a region small enough, which means the density was high enough, then a black hole would form. And at that point, as he tried to do the calculation, Einstein's theory broke down, and we call that point a singularity. All right, it's actually a point in space where the laws of physics don't work anymore. We don't really know what those laws are, and even Einstein's theory don't really describe what's happening well. Further away from that singularity, which is the actual point where all the mass is concentrated, there's a region further away, and we call that the event horizon. We're going to talk about this. So the event horizon is the point within which no light can escape from around that singularity. Outside of the event horizon, light will be impacted and bent around. So light might even go into kind of orbit on this bent curved space, but it can still escape if you want to. So that's really what we mean by a black hole. A black hole, if you could see, it really has three main parts. The actual thing, which is the mass, and it really is something with mass, real matter, is called the singularity. We never see that. The singularity is at the very center of the black hole. General relativity breaks down. Gravity actually becomes infinite at that singularity. Singularity is actually a mathematical definition for what's happening in our equations and how gravity works. We don't really know what the universe is like at the point of the singularity. The event horizon is some distance away. We'll talk about how far away that is. It's not very big. It's the so-called point of no return of a black hole. The shadow, it's the point inside of which nothing, not even light, can escape. So it's the spherical region around the singularity. Anything within that is the region, anything within that, nothing can escape from it, not even light. Because remember, the escape velocity got smaller and smaller as you got further away. So as you move further away from the singularity, the escape velocity is getting lower and lower and lower. And then right at the event horizon, the escape velocity drops below the speed of light, and then light can actually escape from that event horizon. And then these black holes are always going to be accompanied by what we call an accretion disk. An accretion disk is just a disk of matter, which is being kind of like water swirling down a drain. It's matter swirling around and spiraling into the black hole to disappear into the event horizon and then be consumed by the black hole. So this is matter that you can usually see. It's giving off energy. So if you ever see a black hole, it would be this matter from the accretion disk, which is falling into the black hole, that would be visible. The black hole itself, of course, would not be visible. So how big is this thing? I promised you that we would talk about the size. Well, they're actually not that big, but of course it depends on what you mean by the size of the black hole. If you mean the event horizon, which in this case would be, again, it's this kind of spherical object, this little surface here. This is the surface that no light can escape from, and that's the radius. And so the radius of the event horizon is sometimes called the Schwarzschild radius. There's a very simple equation for it. The Schwarzschild radius, R sub s, is equal to 2 times Newton's gravitational constant times the mass of the black hole divided by the speed of light squared. It's just a kind of not really important for you to know, but you can see that mathematics is not all that complicated. It is the physical size of the black part of the black hole. At that distance, which is the Schwarzschild radius, which we sometimes call the event horizon of the black hole, the escape velocity exactly equals the speed of light. All right, so it's a very firm definition for what that means. When you do this calculation, and these things are basically known, you plug in the numbers and you get something like 3 kilometers per solar mass. So it depends on how massive the black hole is, but they're not really that massive. So a typical black hole, for example, might be 3 times the mass of our sun. So if it's 3 kilometers per solar mass, so 3 times 3, it's about a radius of just 10 kilometers. Again, the size of a small town. These are not big objects out in space. They're really not. 10 kilometers is a really compact astronomical object, not that big. If you mean the singularity, which is another part of the black hole, it's the physical size of all the matter stuff in the middle that's warping space and time. Remember, the event horizon is just an arbitrary distance away. The actual stuff that's bending space-time is the singularity. The answer is no one knows. The matter is only 3 to 10 times more than the mass of our sun, so it's not a huge amount of matter, but it's packed into an almost infinitely small point. How big is that singularity? We don't know, because our laws of physics we know are not accurate there. It's got to be smaller than the Earth for sure. It's almost certainly smaller than the size of a pea. It might even be infinitely small, if such a thing is possible. A singularity actually means it's a point source. It's a source of no spatial extent. We just don't know. It certainly is very, 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 very small. Our physics is just not good enough right now to actually know how big that singularity is. We know that time stops at the singularity, and Einstein rules are broken, so we need new rules. That's why we just don't know what's going on at the singularity. When there is no time anymore, when space is that warped, what does it actually even mean to have size? We just need new rules at that point. It's a very, very, very strange place to be. So where does a black hole come from? So now we know what they are, we know what their size is, and the last thing we want to understand is, where do they actually come from? Where, how do these things come to be? Is it likely that a black hole is just going to pop into existence in my office someday? No, not likely. The black holes that I've been talking about are coming from dying massive stars, and we call these supernova. At the end of a massive star's lifetime, after they burned up and used most of their nuclear fuel, they end their existence by exploding and scattering their material throughout the rest of the galaxy. And that is usually the death of a dying massive star. It's called a supernova. So let's try to be astronomers here. Let's pretend that we are observational astronomers here for a little bit, and we're going to play a game of can you spot the supernova? So this is audience participation time. Look carefully at the screen in front of you. This is a real astronomical image. This is not made up data, and this is not an artist drawing. This is an actual galaxy. And I'm going to show you the picture of this galaxy before and after a star has gone supernova. And you tell me if you can see it. And what I'm going to do is blink back and forth between this original image and the image that has the supernova in it. And I'm asking you as an amateur astronomer, can you spot the supernova? So here we go. So these objects are blinking. I'm going to let you look at it for a little bit. Look carefully at the entire image and tell me if you can spot the supernova in this image. In one image, the supernova is there. In the other image, the supernova is not. I'll give you a few more seconds, and then I'm going to give you the answer so you can rewind quickly if you haven't found it yet and you want to keep playing the game and find it. I'm going to show you where it is right now. There it is, right within this yellow circuit. Now, when you see it, you can't almost not see it, right? See that white dot that's blinking into existence? That white dot is one star which has exploded. Frequently, when we see supernova in other galaxies, the light output of that star at the time of the supernova is greater than the output of the entire galaxy altogether, which is an amazing amount of energy. That one star at the moment of its death gives off more energy, more light than all of the other billions and billions of stars that make up that galaxy altogether. Is amazing. And you can see this in that image. That's an incredibly bright spot in the middle of that yellow circle. That's one star. Whereas if you take any other region, if I had moved that yellow circle anywhere else in this image, that will be millions and billions of stars within that image. And that one spot is easily brighter than all of those. So that's how much energy is released in a supernova. So what happens after the supernova? Well, it depends on the initial mass of the star. And of course, you guys have gone outside in the night, you look up in the sky, you see the stars. Each of those stars is going to die at some point in the very, very far future. What happens at the end of that star's lifetime? Well, if the star had an initial mass of 12 to 40 times the mass of the sun. Here's a cool little astronomical symbol, which means the mass of our sun, astronomical lingo there. If the star had an initial mass of 12 to 40 times heavier than our sun, when it dies, it will go supernova for sure. And then what's left behind will be a neutron star. The supernova is an explosion. Most of the matter goes flying and is lost and redistributed out through the rest of the galaxy. There is some little bit of matter left behind. That matter that's left behind forms a neutron star. And the final mass of the stuff that's left behind is going to be less than 3 times the mass of our sun. So it's initially 12 to 40 times the mass of the sun. It blows up. Everything else goes flying through the galaxy. The stuff that stays behind, less than 3 times the mass of our sun, usually somewhere in the area of 1.4 to 3 times the mass of our sun. It's not that heavy, but its radius is very, very small. It's, as I said, only about 10 kilometers big. So its density is extremely dense. It's not so much mass, but it's packed into a really small spot. And that just gives it incredible amounts of density. And its surface gravity is tremendous. It's a massive amount of surface gravity. Its escape velocity is almost about half of the speed of light. And that'll be a neutron star. And we do observe these objects in our universe. But if that dying star had an initial mass greater than about 40 times the mass of our star, that mass of our sun, so initial mass greater than 40 times the mass of our sun, it also will go supernova. But what happens after the supernova, the stuff that gets left behind is going to collapse and form a black hole. So if after the supernova goes and the matter is sprayed throughout the galaxy, if the final stuff that gets left behind is greater than 3 times the mass of our sun, it's all going to start condensing. It wants to be a neutron star, right? It wants to be this compact object, which is a neutron star, but there's just so much mass in it that not even the neutron degeneracy pressure can hold it up anymore. There's nothing to keep it apart. It all wants to collapse to a single infinitely small point. And it's just the force of gravity is so strong. So it collapses to what we said before we think is zero radius. We don't know the spatial extent. It could be infinitely small. Not exactly sure. We believe in the calculations in our math, it collapses to a point that has zero radius and thus infinite density. And that's what we call the singularity. That's the black hole, and that's where it came from. A supermassive star at the end of its lifetime that has blown up, sprayed most of its mass throughout the galaxy, a little bit stays behind, and the stuff that stays behind collapses to a point of zero radius and infinite density. That's called a singularity. The space around it is now warped to form this thing called a black hole. This is kind of interesting. You can actually see what we think is the formation of a black hole astronomically. This is pretty cool. This is a pair of visible light and near-infrared Hubble Space Telescope photos taken before and after an exploding star vanished and formed what we believe is a black hole. So this image on the left was taken in 2007. It shows a 25 solar mass star as it looked in about 2007. In 2009, it went supernova. The star shot up in brightness to become over 1 million times more luminous than our sun. That is a supernova. When they looked again in 2015, 8 years later, gone. A small amount of infrared light was detected from where the star used to be. It's just gone. Where did it go? Things don't just disappear in our universe. If it has gone dark, that is most likely the signature of a black hole. The fact that it got very, very, very bright in 2009 tells you it was going supernova. That was that point in time when it's actually blasting its mass out into the galaxy. That takes some amount of time. After that mass disappears, the stuff that's left behind contracts and condenses and forms a black hole, which of course, as we said, we cannot see because it's a black hole. Light can't escape from it, so it has no visible signature anymore. This black hole is located 22 million light years away in a different galaxy than ours. It's a long, long ways away. But that's so cool that we can actually see with the Hubble Space Telescope a black hole being born in our universe. One last thing that I just wanted to comment on, because there's a lot of misconception about black holes, is that some people think a black hole is like a cosmic vacuum cleaner. It just, once a black hole gets born, it's going to start sucking everything into it and just like eat up the entire universe. That's not true. The mass of a black hole, we said, is only a few times the mass of our sun, which is actually not that heavy, right? These things came from objects that are like 20, 30, 40 times the mass of our sun. The black hole itself is only greater than 3 times, maybe 3 to 10 times the mass of our sun. It's just not that heavy. So if you're far away from a black hole, gravity would be just the same as if you were orbiting a star of the same mass. So it's not any different than any other type of gravitational object. It's only when you're very, very close to the singularity that space and time is warped really strongly. If you get away like the distance that our Earth is away from a sun, you would be fine. For example, if I could snap my fingers right now and make our sun become a black hole, other than everything getting dark, we would not notice it. It doesn't like start sucking in stuff anything differently, right? Because it's just normal gravity. It's just gravity in such a small, dense spot that space gets warped and forms this black hole. We're very, very far away from our sun. We would not notice at all. Earth would continue to orbit this object, Mars, just like before. All right, so it's not anything new. It doesn't start sucking on space around it and eating it up like a giant black hole monster. It's just a gravitational object. In the region of space around it, close to the black hole, as in the radius is less than 3 times the Schwarzschild radius, there are no stable orbits, and all matter will eventually get sucked in. So that's what this picture is showing here. Yes, near the event horizon, and this is saying like about 3 times the event horizon, which is the Schwarzschild radius, then there isn't a stable orbit there, and eventually that's going to spiral in, like you're showing here, and that matter will get incorporated into the black hole. But that's stuff that's really, really close. Remember, the Schwarzschild radius is like 10 kilometers. So that's like what, 10, 20, 30, 40, 100 kilometers? That's nothing, right? Astronomical distances are millions and tens of millions and billions of kilometers. So something like 10, 20, 30 kilometers is just nothing. It's not going to be eating up planets, anything like that. So that's just one way of thinking about a black hole, that it really is an unusual object in our universe. So let me end this talk now just by saying this. This is kind of what motivated this talk and what we got started with. At the heart of every galaxy, there lurks a supermassive black hole. And these we actually can see. This is a different thing altogether. All right, so what I started talking about with you at the beginning of this little discussion was the supermassive black hole at the center of our galaxy. Here's another image. This is actually the first image ever taken in 2019. This is a supermassive black hole that was recorded using the Event Horizon Telescope. And it shows the shadow of a supermassive black hole at the heart of the M87 or Messier 87 galaxy. This is a very large object. It has a mass of about 2.4 billion times the mass of our sun. Remember, I said a normal black hole is about anything greater than 3 times the mass of our sun. This is 2.4 billion times the mass of our sun. Because its mass is so big, its diameter is also extremely large, about 38 billion kilometers in diameter. A regular black hole, what did we say? It's about 10, 20 kilometers in diameter, about 20 kilometers in diameter. This is 38 billion kilometers, okay? That's what we mean by a supermassive black hole. That's a very different type of object than the lone singularity black holes that we were talking about in this discussion. But we now can see them. We can see them because they are so big. So what I would like to do at some point in the future is maybe circle back and continue this conversation and say, okay, we now understand what an isolated black hole is. Is there any way we can understand what these supermassive black holes at the center of our galaxies are actually doing? Where did they come from? And what's their future going to be? I think we should leave that. That'll be a conversation for a future day. So with that, I'll thank you for joining me today. Hope you learned a little bit of something about our black holes. I definitely hope that you will join us again for another DoD K-12 STEM Saturday. I'm really looking forward to talking with you about it. I hope we get to continue this conversation, and I'm looking forward to that a lot. All right, everyone, take care. I'll see you later.